Okay, well, I hope you guys survived the snowstorm and are recovering from all of your shoveling if you had to do that. So the plan for today is to pick up with where we left things last Wednesday, which was dealing with some induction proofs. We were kind of in the midst of doing this extension of De Morgan's law. So before I get started, were there any questions on things? So your homework assignment is now due this evening instead of Monday, so don't forget about that. And otherwise, we kind of just shifted things by a day. So next week's homework will be due on Wednesday also, as far as that is concerned, and that will be some more work on induction. Okay, so let's see if this works. Hopefully it still does. So I'm opening up worksheet 13, where we were. Does that just look black to you guys, or is that, can you see anything? No. Okay.
It just looks black, yeah. Also, when will we be going back to homeworks due on Monday, or are they going to be due on Wednesday from now
on? So we'll for now they're due on Wednesday. We'll see what else has in store for us, and maybe they'll shift again. But this week's is Wednesday. Next week's is due Wednesday as well.
Okay, thank you.
Yep. Okay, so I think that you can now see this. Is that right? Okay. Okay, and so we were working with the extension of De Morgan's law. So we wanted to show that if we take the union of any arbitrary number of sets, n different sets, and take the complement of that union, that is going to equal the intersection of all of the complements. Last time you worked on this in groups, we talked about how in the base case that we've proven this. This is just De Morgan's law, so we don't need to reprove this. We could just state that this is De Morgan's law. And we were working on the induction step, and I think that's about where we stopped. We didn't get too far into this process. But for the induction step, first sentence over here, which is in red, we would just state the induction hypothesis, which is we're going to assume that this property is true for all integers up to but not including some arbitrary integer n. So in other words, this is true for small integers. And then what we want to prove is that if it holds for smaller values of integers, that that is going to be all we need to prove that it's going to hold for subsequent integers, for larger valued integers. And there are different ways that we can try and do that. What's been working so far is, well, if we assume it works for everything up to including k, then let's let n be the very next domino in the chain. So let's let n be the very next integer and try and show if it works for that. That this is going to equal the intersection of all of those complements. So that's what we're hoping to prove. I can't claim that, right? Because again, we don't know that that is true for n. We just know it's true for all integers k and below. So what we can do is, okay, let's plug in our new value over here. We're setting n equal to k plus 1. And with induction, it often helps to kind of write out the first k things and then add the k plus 1 thing on at the end. And then we might see how we can try and use induction in this process. So I think this is about as far as we got. Does somebody want to kind of walk through what you might have come up with a week ago? I know it's been, we've had a break. But I think that there was some progress in the groups on this one, from what I recall. So
I think our group actually did get through all of it.
Okay. So how did you guys? Do you mind sharing how you did it?
Not at all. So basically, after this point that you have written, 1 second, let me get the annotate out. uh, After this point that you have written here,
Uh-huh.
we combined A union or A1 union A2 union all of this section
Okay. Yeah, my pen, I
into
think my pen is a bit slower than the annotate. There we go. That stuff
yep,
there. Okay.
that stuff there.
Uh-huh.
We combined it into the K part of it above, right? So we made it what is it? The intersection or made it equal to the K section of it. Does that make sense?
So
Or
sorry, I'm just writing something. There's just a delay between what I'm writing there. So I'm going to call all of those things X. I'm just going to call that set X. You can call it whatever you like. And there's more coming. There we go. And then we're going to union that with the AK plus 1 at the end.
exactly, which then gives us the same thing as A1 union A2, or the complement of A1 union A2, which
Yeah,
will then show that we can do it with N.
Yeah, so here we're looking at the union of two sets and then taking the complement, right?
Yes.
And that's exactly what the base case, we already proved that for two sets, we know this is true. This is De Morgan's law. That's right. So now I'm just calling that big collection of sets X. And now we can use De Morgan's law on that part by saying this is going to equal the intersection of that. So we're using induction to do that because that's the case where n is 2. Yeah. Okay. And then I'm sorry. And then what did you say next, McKenna?
I was just saying that by reducing it to basically the base case, we can then infer the rest by induction that it is or that it is possible with N as a value or for values larger than K.
Yeah, so we've got a little bit of work to do still, right? So I still want to get down to that point. And so far I've got X complement intersect AK plus 1 complement.
Well, we can make it A to the N or make A or A K plus 1 A N and yeah, let it equal and then
Yeah, so I see how we're going to get this out. My question is, where's all this stuff going to, how are we going to deal with all of the, all of that stuff?
we've already shown that A K or A dot 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 to AK is true for, or it's equal to the intersection one. That the union one's also equal to the intersection one. So we've already shown that. So we can sub that in for X.
Yeah, so over here, X was the first K sets unioned and then complemented. So basically, so far, all we've got is X bar intersect that. So first we were just saying, okay, we can treat the first K sets as one big set. Now we can use De Morgan's law on two sets. So that's what allowed us to go from there to there. So this is kind of the case for n equals 2. Okay. So that's what allowed us to do that. And so now we've got this set up over here. And what Max was saying is this is also De Morgan's law for n equals k. So we can use induction now since we know that it's true for all integers less than or equal to k. So our assumption is that we can say for cases when k is smaller than n, that we can break up that complement into the intersection of a bunch of complements. And then we've got this tacked on the end, which then gives us exactly what we get down here. So down here, we're just using the fact that k plus 1, that was exactly our value for it. But any questions? So here, we actually needed to do induction 2 times. And so what's kind of important here is that we actually needed like 2 dominoes to knock over the k plus 1 domino. It wasn't just the assumption that it works for n equals k, but in fact, we needed the induction hypothesis to claim that this is going to work for all values of k less than n. So that would allow us to use the case n equals 2, 3, 4, 5, and 6. So here, we needed to use 2 cases here, this one and this one. And so that's why it's important in our induction step that we've stated that this is going to be true for all of those values of k, since we might need more than one. So we used it for n equals 2 over here to break up this. We used it on all of these first k sets to get us this, and then that was what we wanted to show. Any questions about that one? And it's nice just to say something like thus by induction, we've proven this is true for all values of n. Okay, any questions? Okay, well then let's strategize about this one, question number 6, together. So now the claim is, okay, if x is the set of the first n natural numbers, then the cardinality, remember this absolute value around the set is telling us the cardinality, which is like the number of elements in the set, is going to equal 2 to the power of n.
I had a quick question about this question because it was part of the quiz that we took before this class.
Okay.
We always assume that little n implies a natural number.
No, you shouldn't imply that. So yeah, that should be like stated for n in the natural numbers or for positive integers n. Yeah, I think that part was assumed here just because like this entire sheet has been on induction. But yeah, that's something that should be stated. Yeah.
With induction, we're always using natural numbers with that, right?
Not necessarily.
Really?
I mean, you're using integers. There could be cases where you're also considering negative integers. I don't think like that's something we'll encounter right now, but in general, you could apply it to situations where you're dealing with negative integers too.
But it has to be where it's going in one direction or the other, right? We can't have or do induction with an infinity in both directions.
You could.
Okay.
Yeah, that we won't see something like that, but that's possible to do as well. Yeah.
Would you then kind of do a cases thing where you would do it in each direction with that?
Yeah, then you might want to do. Yeah, that, I mean that's beyond the kind of what we're at with induction
Of course.
at the
I'm
moment.
just curious.
Yeah. So there are various ways that you might want to do that. But for us, we're just going to be dealing with n being going off in one direction. So sometimes it might not always start at 1. It might start at 0. It might start like this one started at 2, for example, because it didn't make sense to even have this property until we have 2 sets. So yeah, but we're going to be trying to prove an infinite number of cases, and that infinite is just going to be going for n getting larger and larger and larger. Those are good questions. Yeah. Okay, so for this notation around the power set of X. Again, this is what we call the cardinality of the set. And it's going to tell us, in general, the number of elements. Okay, so yeah, so let's kind of start here with the base case, which would be let n equals 1. So if n is equal to 1, then our set X, right, is just the set containing 1. Then we would get the power set of X contains the empty set, the set containing 1, and that's it. So the power set of X, excuse me, right, does in fact contain 2 elements. That would be 2 to the first power. Yeah, was there a question? Or is that
Yeah, it's me again.
Yep, what's up?
Wouldn't the first part of that question, the if statement, wouldn't that basically be saying that where it says X is equal to the set 1 through n, wouldn't that basically be saying that it's the natural numbers?
That so the natural numbers are infinite, right? Where this is a finite set. So we're dealing with a finite subset of the natural numbers. That's what X is.
Okay. But since we don't have, I mean, a specific n, since n is a variable, wouldn't that mean that n could be anything from 1 to infinity?
That's right. But it's finite. N is finite. Yeah. N is a number. Infinity is not a number, right? So infinity is something that a number can approach.
Gotcha. Thank you.
Yeah. So that's a subtle difference that we'll get back to it towards the end of the semester. But n is a finite number. It just could be arbitrarily large. Yeah. Okay, so for the base case, we start with our first value for n, which would be 1, and we just prove that whatever the property is, it works. And so that is the case here. Then we can move on to the induction step. And so here, we're going to assume that the statement holds for all values from 1 up to, but not including n. So we're going to suppose that if we have a set of the first k natural numbers, here we are in the induction step of this proof. So we have the base case, and now we're going to claim that this property holds for integers from 1 up to n. Okay. And then what the goal here would be is we would want to show this is true for larger values of k, or for n, we could say. So what's been working so far is let's try and just set n to be the very next integer and see if we can prove it for that one. And so if we set n to be k plus 1, then we have this set x, right, is going to be 1, 2, all the way up to n, which we now set to be k plus 1. Okay, and so we want to kind of think about how we can use this induction hypothesis to try and prove it for this case over here. So I know what I can say about how many subsets we have with these elements in it, right? So anybody have any thoughts about what we might try and do here? So here's something to think about. So this power set of X consists of subsets of X. So we can think about this as all of the subsets that contain k plus 1, and then union that with subsets that don't contain k plus 1.
So I'm thinking for all of the power set that leads from 1 to k, the induction hypothesis was that it was.
So sorry, so for the induction hypothesis, do you mind repeating that, Mitchell?
I was just thinking that for the power set that includes 1 through k, it was 2 to the k. And then outside of that, we have an additional one. So it would be 2 to the k times 2 to the k, which would be 2 to the k plus 1.
Yeah, I think you're moving in the right direction. So we know that if we think about the set from 1 to up to k, that this has a total of 2 to the k elements in it, right? That by induction hypothesis. So if we think about all of the subsets that don't contain k plus 1, right, that's the same thing as saying all of the subsets of the set of integers from 1 up to k. So we're just kind of spitballing here, just throwing out some ideas that we'll organize, but for the subsets that don't contain plus 1, these would be all the subsets of the first k integers by induction there's 2 to the k of those. And then there was a second part of your thought process, Mitchell. Sorry, you volunteered, so I'm going to keep you on the microphone here. So what was the second part of that?
So the second part was if we assume that the 2 to k to be true, adding another one is just 2 to the first power. And then multiplying 2 to the first power times 2 times k equals 2 to the k plus 1, which equals n.
Okay, so you're thinking about how we can quantify all of this stuff over here? Is that the idea?
I think so.
Yeah, so you're right in the sense that what we're hoping to show here for the case of n being k plus 1 is that we're going to hope to show that there's a total of 2 to the k plus 1 elements. We've got 2 to the k over here. So we need another multiple of 2 really, right, is what we're missing. And that's going to come from these over here. But if you think about it, any subset, just going to write some random facts here and we'll clean this up. So any subset of X, okay, which is this entire thing over here, so any subset of X that's going to contain the element, the number k plus 1, we can think about that as taking some subset that didn't contain k plus 1 and just sticking k plus 1 into it, right? So that means, how many subsets contain k plus 1 is going to be the same number of subsets that we had over here. So that means we have 2 to the k subsets over here. We have 2 to the k additional subsets over here, and that would make up all of the subsets of X, since either those subsets contain k plus 1 or they don't. So what we've got is, therefore, the power set of X contains 2 to the k elements that we get from here, plus another 2 to the k elements that we get over here. So that all adds up to 2 times 2 to the k, right? I could factor out 2 to the k, which is where the 2 to the k plus 1 comes from. Okay, any questions about that? Okay, hold on, give me one sec. Okay, so I will leave it for you guys to try and organize that, like in paragraph form. I'll put up a final version as well, but I think it's good practice to try and write that up on your own. But any last questions about that one? Yeah, so I caught some discussion as I was coming back into the room about something being a bonus. So if you guys were asking about this question over here, yeah, this is on the homework assignment. You can think about this as like an option. If you didn't get this one, that's okay. You won't lose points on it. If you did go for it and you did it correctly, then you'll get some bonus points for that. And so that's also, I'll just leave that one there. That's a bit trickier. And we just did this one. So I think the only one that we haven't done was this one over here. We kind of skipped over this one last time. So let's think about this one. So maybe I'll have you guys maybe think about talking about this in some groups. So here a punctured 2n by 2n checkerboard just means we have a checkerboard which is a square, and the number of squares that make up each side is some power of 2. So this would be 1 by 2 to the 1 by 2 to the 1 checkerboard. Since each side consists of 2 things, right? And then we puncture it out over here. This would be an example of a 2 squared by 2 squared board because we have 4 by 4, right? And then we poke out 1 square from that checkerboard. And so this is just showing how we could tile a 2 to the 2 by 2 to the 2 checkerboard. So the claim here is this can be done for any value of n, from n bigger than or equal to 1. So the next one to think about would be like a 2 by 2 to the third, which would be, 2, 3, 4, 5, 6, 7, 8. And then you would have 8 things this way. I am not drawing the whole thing, it'd be kind of big, and then you would just poke out 1 square somewhere from that checkerboard. So again, the claim here is that we can tile this for any value of n with these L triominoes. That's what this little piece is called over here. So So let's kind of just set up the plan. Maybe we can talk about the induction hypothesis and what we would want to prove. And then I'll give you guys a chance to kind of brainstorm some ideas. But for us here, the base case would be setting n is equal to 1. And that is pretty much this one over here. So if we let n equal 1, then this punctured 2 to the first by 2 to the first checkerboard results in a single L triomino. That's the one up here. So we can tile it with 1. Okay, questions? And then we'll go into the induction step. Okay, and we're going to assume that this punctured 2 to the k by 2 to the k checkerboard, that can be tiled with L triominoes for all integers from k up to but not including n. And I'll just kind of say this succinctly, that we want to prove this is true for n bigger than k. And so let's try the very next size up, which would be a k plus 1, a 2k plus 1 by 2k plus 1. So let's think of the following scenario. So let's say we have a 2 to the k plus 1 to 2 to the k plus 1 checkerboard. So I haven't drawn all of these boxes in, but this just means we have 2 to the k plus 1 squares going along this direction, and then we have another 2 to the k plus 1 squares going over here. So recall, right, 2 to the k plus 1, that's the same thing as 2 to the k plus 2 to the k, right? So I can break this up into 4 2 to the k by 2 to the k checkerboards, right? We haven't punctured anything yet. That's what I mean by this. So here we can break this entire 2 to the k plus 1 times 2 to the k plus 1 up into 4 different 2 to the k by 2 to the k checkerboards. That's kind of the key observation here to get that induction process going. Any questions about the kind of arithmetic about why these 4 2 to the k by 2 to the k's is equivalent to 1 2 to the k plus 1 by 2 to the k plus 1? Okay, so then my suggestion would be we need to puncture this, right? And so I'm going to use the old without loss of generality. Doesn't matter where I puncture this. So let's just say I puncture it right here. So that means we've taken one square out of that 2 to the k by 2 to the k checkerboard. Which would mean that by induction, we can checker this. We can tile it with L triominoes. I'm not going to do it, but that's what our induction hypothesis would say. So we've got this piece taken care of, right? At least we've got that part of the checkerboard taken care of. And the question is, how can we checker, how can we tile these three with L triominoes? And so my hint would be to place one of these L triominoes someplace convenient. So at this point, we don't need to place it in here since this bottom one has been taken care of. So there should be a really strategic place that you can put one of these pieces that's then going to allow you to do induction on the other three remaining pieces, similar to how we were able to use induction over here. So what you might want to think about with your group mates, well, first of all, just make sure the way that we've broken this up so far makes sense. And if you're comfortable with, okay, I'm cool with how we broke this up into 4 different pieces. I'm cool with how we can use induction on this one over here. Make sure you guys are okay with that. And if that makes sense, then maybe start to think about where is a nice place that we could put our first L triomino if we wanted to start to think about how we can tile these other 3 sections of it. Okay, make sense? At least what the topic of discussion should be. Okay, that's good. Let me open up the breakout rooms then. And maybe let's spend about 5 minutes or so just trying to see if you can think about a strategy for these. Okay, so rooms are open, and yeah, so Lindsay and I will be checking in on you guys as you're talking about these. Thanks. Okay, well, welcome back, everybody. Kate, and since it was your idea, do you mind sharing everybody what your plan was, and I can try and
yeah, I can do that.
Sure.
So what we were thinking, right, is that from our induction step, we know that if we can just take one little tile or whatever out of each of these boxes, right, that we can pretty much just use induction to solve it from there. So what we
Sorry.
need to
Just
do is
gonna,
figure
sorry,
out a
Kaden.
way.
So just
Oh,
to back up, if I had it like this, right? By induction, we could tile this because each of those 4 pieces has one thing punctured out. So by induction, we can tile a 2K by 2K punctured checkerboard with El Triomino. So if it were like this, if we had one puncture in each of these, we're good to go. However, we start with only one puncture. Yeah.
So what we kind of decided on was that because like our little tridomino pieces each have like 3 spots in them, if you could create one where each spot was in a different box out of our 3 remaining boxes, then that would give you one piece taken out of each of the 3 boxes. So then you could use induction the rest of the way.
Yeah. Excellent. So the idea is, right, here's an L triomino right here, right? That just means it consists of 3 squares in an L-shaped thing. And so we started with one puncture, and it doesn't really matter which one of these places we put it in. So we put it down here. Good. This one's tiled by induction. Now I need to tile these other 3 areas. So if I think very strategically about where I place the very next L triomino, then I can use induction on the others. That's right. And so the suggestion here is if I place my very next one right here so that it in essence acts as puncturing out one square from each of these 3, right? These checkerboards now have one square punctured out. And by induction, I can checker this because it's 2 to the K by 2 to the K with one puncture. I can checker that, and I can checker that. So this one we could puncture, we could checker because it started with a puncture. And now after I tile this one, the very next one I'm going to put in a way that punctures each of the other remaining pieces with one square. And now I don't need to worry exactly how I'm going to place all the other El Triaminos. I can just use induction that it's possible without saying exactly how I'm going to do it. Okay, so we'll stop here. We're out of time for today, and so we'll pick up on Monday doing some more induction. So we're going to spend all day Monday doing more induction problems, where things might not. There might be more than one base case that we need to show, or we might need a couple of induction things in order to prove the general case. So we'll work with some inequality. So we'll do other types of induction on Monday. Yeah, so if I don't see you guys, have a nice weekend. Good luck getting your homework done for this evening. And I'll see you guys on Monday.